Einstein, 1933. There are certain occupations, even in modern society, which entail living in isolation and do not require great physical or intellectual effort. Such occupations as the service of lighthouses and lightships come to mind. Solitude, Einstein argued, would be perfect for the young scientist engaged with philosophical and mathematical problems. His own youth, we are tempted to speculate, might be thought of this way, reading the Berne Patent Office, where he had earned a living, as no more than such a distant oceanic lightship. Consistent with this picture of otherworldliness, we have enshrined Einstein as the philosopher-scientist who, unmindful of the noise from his office work, rethought the foundations of his discipline and toppled the Newtonian absolutes of space and time. Einstein's removal of these philosophical absolutes was more than a contribution to relativity. It has become a symbol of the overthrow of one philosophical epoch for another. To physicists like Henri Poincaré and Hendrik Lorentz, Einstein's special relativity was at first startling, almost incomprehensible, because it began with basic assumptions about the behavior of clocks, rulers, and bodies in force-free motion. It began, in short, by assuming what these physicists had hoped to prove with their own very different starting assumptions about the structure of the electron, the nature of forces that connected them, and the dynamics of objects moving through the ether. As we will see in subsequent presentations, it wasn't long before a new generation of physicists, including Werner Heisenberg and Niels Bohr, patterned its quantum epistemology around Einstein's almost operational definitions of space and time in terms of measuring with rulers and coordinated clocks. For the philosophers of the Vienna Circle, those pioneers of a new philosophy of science, including Moritz Schlick, Rudolf Carnap, Philipp Frank, Einstein's special relativity paper was also a turning point, an ever-present banner to be flown for a scientific philosophy that would put every concept to the test the way Einstein had with space and time. Einstein begins his thinking about relativity invoking Galileo. He is thinking, as so many physicists at the time were, that all the way back when Galileo was doing his physics, you had a principle of relativity. If you were constantly moving, Galileo imagined traveling in a sealed cabin on a sailing ship on a smooth Mediterranean Sea, the wind blowing at constant speed, and nothing you could do in that cabin would reveal that you were in motion. You could have a fish swim in a tank of water, you could have drops splash over, you could bounce a ball. Whatever you did would be indistinguishable from the way the same scene would take place were that cabin located on dry land. Now, the problem was that when you came to questions of electricity and magnetism and the way they combined, for instance, to make electric waves, this didn't seem to work. Why? Because Maxwell, back in the 19th century, had predicted that you could actually make electric waves that would travel along and that they were nothing other than light. Light was just these electric waves. Well, Maxwell thought, everyone thought, that if you had a wave, it had to be a wave in something. Well, what was the medium in which these electric waves traveled? Well, it wasn't air, because we see the sun, and that travels through empty space. So they said there must be something, let's call it the ether, which is everywhere. And that ether supports the waves that are, in fact, light. So people wondered, is it really true that it wouldn't matter if you were moving at constant speed through the ether? Well, it did seem like it should matter. It would be like racing through the desert on a flat car with the wind in your face. What if you shot a light wave into the ether as you were racing across it? Wouldn't that be different than just being at rest in the ether and sending the wave along its way? Well, this bothered different people in different ways. Maybe you would need to make little corrections when you were moving through the ether. But Einstein had a different picture. He wanted the principle of relativity that Galileo had enunciated to be true for all of physics, and there was something that bothered him very specifically. In particular, suppose you have a coil and a magnet moving towards it. If we imagine the coil at rest in the ether, then the magnet moving towards it makes an electric field, and you have one explanation from Maxwell about what's going on. Maxwell says when you move a magnet towards a coil, the magnetic field gets more intense near the coil, and a changing magnetic field makes an electric field. An electric field drags the charges around, sends them to your home, and you can light up a light bulb. So that's one explanation. But what if you take the magnet and fix it in the ether and move the coil towards it? Well, now you have a different explanation. The charges, as they move towards the magnet, experience a force, because moving charges in a magnetic field experience a force according to Maxwell. So you have now a new explanation for why those charges are dragged around. Moving charges in a magnetic field get pulled around. There's no electric field at all. Two explanations depending on which frame of reference you're traveling with. Are you traveling with the magnet or are you traveling with the coil? Einstein says two explanations, but only one phenomenon, one observable thing, namely coil and magnet are approaching, and that bothered him. Einstein hated to have two different representations about what was going on if there was only one observable thing, namely coil and magnet approach, make current, light up light bulb. From that very simple set of reasonings that seemed almost childish to his contemporaries, Einstein said, we need to have one single explanation. We need a principle of relativity like Galileo's that said it doesn't matter which moving frame you're in, the laws of physics are just as much the same for a magnet and coil or light as they would be for a fish swimming in a tub of water.